into quite a bit for the soil structure interaction specifically, and I don't profess to be a geotechnical engineer or SSI specialist. However, the webinar is intended to address some special structural soil structure interaction issues encountered along the way of this project, and perhaps offer some insight into how we approach the challenge with Midas and other tools, and address some items that we possibly need to be aware of for non-pile foundations, and most importantly, initiate some discussion. This is an evolving facet of our industry, subject to many multidisciplined opinions. So with that, I'll get into it a little bit more here. The challenge we had was assessing an ultimate lateral resistance of a caisson for an existing bridge. Although the bridge project discussed is confidential for security reasons, the approach is applicable to a wide range of caisson-based bridges around the nation and the world where capacity is of interest. Our approach was a soil structure interaction employing industry-accepted tools and current theory applicable to large diameter embedded foundations and adaptation of PY criteria. So with that, I'll get into a kind of a quick introduction to the caisson, just for setting the understanding of what generally it is. Some people may or may not be familiar with it. The choice of piled foundations is currently the often go-to solution for many contemporary bridges, including signature bridges. However, before pile technology came along, many iconic bridges built in the last 100 years over a river, bay, or questionable soft soils were built using caissons, which is a French word meaning drawer. Quoting our trusty contemporary crowdsourced dictionary, Wikipedia, a caisson is a watertight retaining structure used on a foundation of a bridge pier and constructed such that the water can be pumped out, keeping the work environment dry. Generally utilized on when suitable sub-foundation is achievable, i.e. not too deep and accessible to the good stratum is relatively accessible. Shallow caissons may be open to the air like a bathtub, while pneumatic caissons, which penetrate soft mud, are sealed at the top and filled with compressed air to keep the mud and water out at depth. An airlock allows access to the chamber while workers move mud and rock debris from the leading edge, which is also the cutting edge, which proceeds downwards towards the depth. Caissons can be built in or floated from a dry dock, ballasted down to a depth, or through soft soil to the stable layer where they can bear. In many pneumatic caissons, workers were often subject to caisson disease, or a case where the bends or decompression sickness for all you scuba divers out there due to the entry and exiting of the compression air vaults. A caisson is effectively a moving form that, once placed in the final position, becomes filled with concrete steel structures and then becomes part of the final structure of the pier. In some ways, it's a giant cookie cutter that doubles as a final foundation mass, some of them often penetrating up to 100 feet into the mud. Most were designed for vertical bearing pressure, not lateral loading, and designed effectively at simplified footings, and many have settled over their times, ignoring skin friction contributions. Just want to go over some of the recognizable U.S. bridges where caissons are part of the superstructure or supported. One of the most infamous ones is the Brooklyn Bridge, and perhaps one of the major first bridge to utilize this, the European technology of the day, which John Roblin's son is credited for application of and his knowledge gained from his time in Europe, where it was used. Basically, there's a 102 foot by 172 foot wide and 22 foot high caisson made of a dense grid of pine and through both, built nearby and sunk using airlocks. There's many fatalities during this sinking of this caisson and afflictions due to decompression disease, which didn't start off this concept on the right footing. Another large project you may be familiar with is the Ben Franklin Bridge, a Ralph Majeski designed bridge with a 70 foot by 143 foot, 40 foot high caisson sunk into place using advances and lessons learned from the Brooklyn Bridge. Luckily, no fatalities were involved in the construction of this caisson. Moving into some other more contemporary bridges, in the Mississippi area we have the Huey P Long Bridge, constructed at River Mile 106 in 1935. It's a very high level steel truss structure utilizing caissons. Also, number 1 and 2 of the Greater New Orleans bridges, at mile number 96. At one point, the main span cantilever steel structure of this one was one of the longest highway cantilever in the world. Also, the Hill Box Bridge, constructed in 1983, is a high-level cable-stayed box girder bridge with the 1,200-foot main span, once the longest in North America. Looking at some other recognizable structures, we have Delaware Memorial Structure. In 1952, this was built with 95 foot by 221 foot wide caisson, sunk to 116 feet. The Tappan Z is an all-cylinder structure with the Walt Whitman, Thurrock's Neck, and Verrazano Narrows bridges, also using some very interesting approaches to caissons. And I would just note that the Verrazano Narrows has a 170 foot deep caisson on the Brooklyn side, achieving some bearing pressures up to 6 tons per square foot. And so you can understand that the size of these caissons is primarily due to the need for bearing pressure. Most recently, the Greenville Bridge in Mississippi, also a 1378 main span. Caissons are footed in and sunken into place using air domes. And on the west coast, the new Tacoma Narrows Bridge is a 5,400 foot long bridge with a 2,800 foot suspension main span, and uses 130 foot by 80 foot by 216 foot tall caissons which penetrate the seabed over 60 feet. These were floated into place and anchored using a very unique and innovative cable anchoring system in currents of up to 7 knots. And actually, it's a fascinating procedure on how they anchored this and used a very elaborate system of cables to keep it anchored and ballasted. You know, and one of the big things about some of these older bridges is that they were generally designed as footings, and with current codes, we are under the responsibility of trying to accommodate lateral loads from, say, ship impact, seismic, other extreme event loads. And so conventional soil structure interaction theory for piles and things can break down, and so you have to take a very innovative approach. So some of this presentation is kind of just going to get into some of how we leverage other soil behaviors and trying to address these issues. For this specific bridge caisson, it's a 1950s multi-span steel bridge, a high-level approach with a main span pier supported on a 66-foot diameter by 52-foot wide caisson. It's embedded into the ground about 70 feet into the mud to a competent clay layer. But what's important to also notice is it's 80 feet in water, so quite deep to the mud line. It's a 90-foot tall pier with a gravity loading of about 40,000 kips, and that's broken down from about 8,000 for the superstructure, 11,000 for the pier, and 21,000 for the caisson. A couple of quick details here showing the cutting edge detail, which is one of the comparable detail on other caissons, and where they're used to proceed and move the caisson to the depth and kind of cut through the mud, the soft mud. And so with a 200-foot tall component, this, you know, the magnitude of it is quite large, and it's something from seeing here, you can fit the Statue of Liberty in it or fit it clear under the Golden Gate Bridge like these cranes are just squeaking under. So very large sizes and magnitudes. And again, 40,000 kips bearing. So we started out with a soil profile submitted by our geotechnical engineer, and which is supported by historical boring information. We didn't actually go and get any borings, but there was some very good information that helped us produce this table. That is pretty much what typical information you'd expect for a bridge foundation. Just a quick isometric of the pier and the caisson itself to show the magnitude and the stratification and the depth of water. Again, it's about 6 tons per square foot under the surface bearing. So the issue really becomes, hey, we've got these information for soil and we have tools available to us. So let's just plug them in and go to it and see how we can have this thing react and respond. So optimistically, we assumed that since we got all this information, we could just go with some program like LPILE or MIDASoft and input all the variables. So our first run at it was basically to input the soil properties and the diameter, the effective diameter of the caisson, which was about 58 feet. So we created the Midas model, and input the information, mainly elastic properties for the caisson, effective diameter. Lateral loading, we started at the water line of about 1,000 kips. And we turned it on and let the model assess it. We used the soil structure interaction module of Midas to produce the initial nonlinear springs that is great with Midas. So the results, very fast, obviously. It's a very simple model in some natures. But we initially found 160 inches of tip displacement. And so when you look at it, you say, is this realistic for 1,000 kips? And the answer is no. So this kind of started us thinking along the process of, well, what's going on here? Is it something to do with Midas? But the same thing was happening in Alpile. So it was something in both programs. So there was something bigger than just these programs, and it was more than just simple soil structure and diameter issues. Which got us thinking about the whole PY curve and the whole story behind it. And so before we get any further, I'd like to take this time to kind of take a look at the PY springs and understand how they work and kind of some background into what they're derived from and how they help us. Fuller and Brom's method in 1965. Well, and we should also mention that the PY springs are generally extensively used by FHWA API and designers worldwide to create soil structure interaction between the substructure and the superstructure by using these nonlinear pile springs at different discretized locations on the pile. A little bit of history about where these things came from. Initially, you had Brom's in 65, which was an ultimate capacity approach. Really no soil modeling, it's just an ultimate capacity. In 1960s, Reese and Matlock started to develop PY springs for studying of sand and clays, and that helped define the approaches that software tools like COM started to develop for the build-up for Alpile and other approaches for soil structure interaction. You can see in here that there was further studies by others along the way, and then API got involved with some sponsored studies in 1983 to kind of look at what a little more closely some of these details and reevaluate some of the studies that had been done to date. They came up with some bases that basically supported the work done by Reese and Matlock and created their own generation of springs that basically supported all this information. So ultimately, they all provide an approach using nonlinear curves relating P soil reaction to Y lateral response. Generally, the information was supported by full-scale pile lateral loading tests. And formulas derived primarily for homogeneous soils. In 1983, an approach by another study, the University of Texas kind of started to look at how we could properly address multi-layers and reactions and responses to soils, which created a different equivalent depth approach, which was also incorporated into Alpile, FB Multipeer, and other software tools to help address the non-homogeneous results and effects of soil layers. So traditionally, PY springs are based on a function of the soil modulus, some of the depth, the projected area, and they're tributarized over the specific width and length of the pile and placed as a node spring. Generally, these are great for predictability and design in highly nonlinear mediums such as soil. However, along the way of the history of the PY spring, there has been some controversy and challenges to where they come from, and are they really giving the full picture of what is happening in the soil strata. So ultimately, the PY spring theories are really supported from field results, which are generally 12-inch to 48-inch diameter piles. Free heads allowing for pile rotation. Fundamental PY curve behavior has been challenged due to noticeable increase in stiffness and very responsive piles larger than 5 feet. And this is kind of accounted for in this Stevens and Audibert in 1979, which suggested perhaps PY modification factor might be the approach to dealing with this. But effectively, information was there that suggested there was more to it than just PY lateral translational springs. Digging deeper, a study conducted by the FHWA in 1986 by Lamb and Martin suggested that by going through a backfitting analysis to conduct the effects of this additional stiffness, they found that rotational stiffness on 5-foot shafts was starting to become noticeable. Skin friction effect contributed to moment resistance while base shear and tip effects also had an effect on how the total global behavior of the caisson was reacting in soil response. Some of the research that came out of that just shows here, you can see the PY only and base shear approach here down in the bottom, and this is more of the measured response you're getting up here. So definitely a lot more stiffness is being attributed to, and these are 5-foot diameter piles. So I think the ultimate take home from this was that there is potential additional effects that may need to be accounted for, and something that may not be accounted for in regular PY springs. Ultimately, their conclusion was that pile rotations and soil rotational response provided a rational account of the apparent increase in soil resistance for large diameter piles. Effectively, using moment data or rotational springs at identical locations as your PY was the apparent recommended approach. And this was effectively indicating a stiffer response with less head deflection and less tip deflection as well. Something to be aware of, especially when you're thinking about seismic or anything where performance-based displacement effects are part of the overall solution and approach. So noticing that these were issues that probably are affecting some 5-foot diameter piles, and probably not as big influence in that area, but imagining the effect on something as magnitude of the 66 feet by 52 feet, you can see the pile, the 5-foot diameter one off to the right there in comparison with the caisson. So clearly there's going to be some sort of effect there, and I think it's a no-brainer to a lot of people that this would be the case. But I think the ultimate understanding is that, you know, we have tools that easily accept the diameter. Okay, let's input it, let's input the soil properties, and off we go. But again, I think we just want to recognize that perhaps the PY approach may not necessarily be directly helping us directly understand the full picture. But clearly, this large caisson may not be acting like we think it is, like a pile. And it's probably, like most of you would say, okay, we can use LPAT for this sort of approach. And a little bit of scale there to get an idea of what size magnitude this thing is. So we enter here with the Midas Civil approach, soil structure interaction module, which is an effective tool offered as an approach to accommodating the subsurface effects of soil for deep foundations. You know, it avoids simplifications such as the point of fixity, which we all know causes iterations between other third-party programs and software to kind of find your solutions for different cases. It minimizes iteration between these other tools and really helps you kind of build your model within one venue. For a better approach to encompassing the soil structure interaction and the superstructure effects and loading. So I wanted to also try to get into a little bit of the engine behind the Midas formulations. I think it's important to kind of understand not necessarily what the black box has, but because they're very clear on what the information is. But it's good to kind of get a clear understanding of the variables that go into the information and how it decides what those springs are and so on and so forth. Real fast, this is a takeaway from the support information for Midas, and you know, basic information like the ground level, elevation, pile diameter, unit weights, air pressure coefficients, and soil modulus. As you can see, this information is recognized as being part of the interaction module. A little bit of information about the lateral springs and really what this is trying to accomplish. Obviously, it's a nonlinear spring it's trying to aim for based on relationships between these values of PK, PM, PU, YK. Effectively, one's for different soil types, sand and clays, and it just walks through the information that goes on to the formulation. And what it seems to indicate is that the clay is based upon Evans and Duncan 1982, which is kind of in line with MATLAB as far as I understand. And calculation of PU in soil for clay is this sort of formulation. You've probably seen this somewhere else, but again, it's in line with industry expectations. Moving into the sand value, this is the formulations here to break it down into the values of the C1, the C5, and C6 constants that are built into the formulation. You probably recognize these. The spring stiffness ultimately is those values, PM, the P values multiplied by the tributary area that end up providing the actual force to displacement nonlinear spring at each discretized notation on the spring. Interesting to note here is that some of these constants used in the formulations for sand, you can note here that the loose, medium, and dense are 20, 60, and 125 PCI respectively. Important to know that those are values that are based upon an approach by Rees, 1974. They're identical to the approach L-Pyle takes, except that it's a sand below the water table condition. So when you're approaching these, the soil structure interaction Midas, be aware that this is the assumption taken for the interaction formulation. For instance, if you wanted to use sand above the water table, you'd probably be looking at a little different stiffness parameters compared to 60 versus 90, so a little bit of different reaction there. And that's something that you might have to be aware of and take advantage of in sort of maybe a multiplier as you take on this in Midas. Vertically, the module uses an elastic spring for vertical spring stiffness based on this basic simple formula here. So keeping in mind, laterally we're using nonlinear springs, and vertically we're using elastic springs. A couple things to be aware of in the module. These are the information supported and provided in the pile for the soil structure interaction is specific to each pile individually. So therefore, if you were looking at a group of piles, you would have to be aware that modifiers would be needed for that as well. You can turn to AASHTO for that kind of group pile modifier information, or your friendly geotechnical engineer is also helpful with that. But effectively, keeping in mind that these effects, such as skin friction and group effects, are not necessarily included in the soil structure interaction that you'd expect, and also very equivalent to L-Pyle, where these effects aren't necessarily approached as well. So in that sense, I'd just say consider PY multipliers to accommodate additional effects if you're working with these groups and also larger diameters, specifically when you get into an area that's beyond the limits of the conventional testing, which is 48 inches. I'd also like to point out that for some of these analyses, some of them are run quite differently. You may have since the response spectrum is something that is kind of a linear static application, how does it deal with nonlinear springs that you have in your model? Well, as Midas breaks it down, effectively response spectrum and eigenvalue analyses convert the springs to elastic linear types in the analyses. But other than that, every other type of analysis would generally utilize nonlinear behavior of your springs. Something to keep in mind as you kind of run through the analyses engine. So for our Caisson approach, the initial approach was elastic. We actually fixed the base, pushed it with 2,500 kips at the mean high water level, and found that basically the Caisson itself didn't have any tensile cracking, and I think that deflection was probably less than half an inch without any soil structure interaction. So we were kind of trying to get a sense of kind of what the loads are and how the response would be. The next stage was to take it into the soil structure interaction module of Midas and apply a base lateral stiffness, which was substantially higher due to the base stiffness suggested by our geotechnical engineer. As a result of that, we started to see about 3.5 inches of deflection at the tip of the pier due to the approach of the soil structure and the base effect. So USAP and Midas to both do that, and they generated very similar results that we felt pretty comfortable with, but understanding that these are very low limits in terms of lateral forces, and also really didn't help us understand the ultimate capacity of the Caisson. It was really just a check of, well, what could be sort of the demand or the behavior to expect for a reasonable load. So really the idea here was to address the ultimate capacity in the soil structure interaction and really understand where non-recoverable plastic deformation could be occurring so that we could properly understand the limits of the structure itself. With that, we basically took on some real and great information and input from our geotechnical engineer, who basically, with the support of current research papers, FLAC validations, and other FEA to verify what we were doing, proposed some approaches to the Caisson soil structure interaction, a large-scale foundation using some soil nonlinearities that we basically generated and created nonlinear springs to input into a structural model. Specifically, we generated nonlinear PY, force displacement, nonlinear springs, so moment theta, nonlinear springs, and also nonlinear base lateral and base rotational nonlinear springs that considered the effects of the overall Caisson behavior embedded in such a massive soil. Nonlinear soil friction curves, T theta, were used with diameter to generate the moment stiffness, rotational stiffnesses. So on the diagram to the right, we're seeing that you're not only dealing with just PY, but you're also dealing with springs that are rotational based up and down the shaft of the caisson. So after the setting up the model for the pushover analysis, we also generated material nonlinearity just to make sure that during the pushover we had incorporated the effects that would be accounted for in the material effects, such as concrete and steel nonlinear models, which were included here. So because of the size of the caisson, there isn't really a cookie cutter shape. We had to generate these, and it took a couple of hours to generate the sections for the pier and the caisson with each rebar in there, and ultimately create your design section that would be used for pushover. Should note that also we looked at the nice thing about Excel and all our other tools that we use. You can create macros and nice parametric approaches to helping use nonlinear data to format it in ways that are nice for exporting and directly copying and pasting into our programs like Midas or SAP through the table use. So the result is a pushover analysis, and this is really just an output of it. It could be in Midas, it could be in SAP, but effectively it shows you where basically elastic behavior occurs up until a certain point, and then it starts to change and go nonlinear. At that point, that's the point we were clearly interested in from an elastic point of view, because this is the location where the behavior beyond is non-recoverable plastic deformation. So effectively up until that point, we captured the realization that lateral loads that we were subjecting to the caisson and the pia structure would provide us with a recoverable deformation up until this loading. And a key point to understand too is that I think the base reaction is shown here, but that's not necessarily the loading that's applied to this being a cantilever. So we take the displacement limit at the elastic level and we put that back into an incremental lateral loading where the load is where we need it to be, and we check that with the pier tip and we back calculate that to the applied lateral loading that we get for the capacity at that elastic limit. Some interesting results that come out of the analysis with the soil springs and the lateral translational and the rotational. Shown here is the lateral Py response. The red line is the yield limit of what we believe the soil to have. The blue line is the response. And you can see that there's quite a lot of capability in the soil to go further in terms of Py, which perhaps is misleading because when you look at the rotational response, you're seeing that you're at your level of lateral force, you are at the ultimate limit, or the plastic limit, or sorry, the elastic limit of the soil and rotational behavior. So looking at both of them, you can see that the Py is giving you a sense that perhaps there's a lot more capacity in there laterally. But when you look at rotational, you're seeing that you're at the limit and you're yielding due to rotational behavior, which is a result of skin friction and sort of the large turning of the caisson within the soil medium. A chart that kind of summarizes some of the response and the pushover results. I just want to kind of focus in on the blue line, which is this main pure Caisson 1S. It shows basically a limit of about 7,100 kips as the elastic limit. And don't get me wrong, I think that it's clear that when you get into seismic or other kind of extreme events, there is more capacity here in terms of ductility. But ultimately, for what we're looking at, we were looking more at the elastic limit. I just want to point out here that the green line and the red line is a output from the analysis for the other Caisson. We removed the rotational springs from that pier and pushed it over, and effectively you can see the difference here. There's probably about a 30% increase in capability and stiffness because of the springs, as you would expect with extra stiffness. But it's just interesting to see the kind of the demand and the capacity and how that may affect your specific project with that result. You know, I want to take a couple of variations and just make sure that we were getting the behavior we were expecting. I think ultimately you know, most of us do a push over the soil structure interaction and we see the plastic hinges forming in the piers. But is it necessarily true? Is it happening? Well, in our case, the soil Caisson was so large that basically the forces were never big enough in the Caisson itself to generate a plastic hinge. So what I tried to do was remove all the soil springs from the model and rerun it, and quite easily you'll see that there is a hinge that can form quite quickly in this. It's about 6 inches versus the 11 noticed in the soil structure interaction. So clearly a little bit more further response laterally, but less stiff, less deflection, and more stiffness here in the no soil structure interaction approach. Placing that back on the graph with the other information, you can see kind of bigger response. Really a lot stiffer, less capacity in terms of different responses. And I think it's key just to understand that. I think that's the whole point of why we do soil structure interactions, to understand why the soil medium affects the response and what we're trying to do and get demand and so on and so forth. So interesting results, I think, from what we gained. Another approach we wanted to take with Midas specifically because we were kind of stuck with the ability to really push Midas with the module that was involved. So we thought, well, maybe the way to do it is with PY multipliers. And so the nice thing about the Midas tool is that the activity between the databases and Excel is quite excellent. So basically taking our initial stab at the soil structure interaction parameters as shown earlier with the diameter, the tributary length, and soil parameters, you can extract the nonlinear information straight from the database, and with a quick multiplier on there in Excel, you can copy paste back your values back into Midas, and before not too long you're running the model again and checking the values. So that was one of the approaches we took to kind of take what we knew is basically our base understanding, or kind of the answer effectively based on the geotechnical verification and the other research just shown previously, and was to take the Midas and kind of push it to see where we'd get to if we were just using the Midas only. Without a PY modifier and a pushover, we're getting about 400 kips of capacity laterally. Now compare that to what we believe with the rotational stiffness and the other effects of 7,000 kips. Quite a big difference in the response there. So clearly a little softer, and this is something you could expect in LPAL as well. Again, going back to the beginning, it's not a Midas issue. This is more of a general PY issue. Taking it up a little notch to a PY modifier of 3, you start to see a little more capacity, 1,000 kips perhaps. Still not getting the capacity we were understanding to be for the project. Taking it further, a 10 multiplier on the P, and again, we're getting up to about 4,000 kips elastic capacity. And one more step to 15, and now we're in the range where we're kind of equivalating that back to what we were looking at earlier. So just side-by-side comparison, PY modifier of 15 sounds substantial, and perhaps it is, but I think considering the size and magnitude of this sort of structure, I think it may not be unreasonable to fathom that, especially given that original research by Landon Martin was indicating that probably a PY multiplier of 1.5 to 5 could be something that's credible. So I just wanted to kind of summarize some of the information here, you know, and really kind of take the big picture look at really what we were finding in this project specifically and how it relates to everything. Ultimately, these are old foundations which were, again, designed for very large bearing forces, generally in the 4 to 6 tons per square foot allowable service bearing pressures, with ultimates probably in the 10 to 12 tons per square foot, perhaps. These are old foundations that, well, combined with current codes, may not necessarily be meeting the new code forces, perhaps if you take them as a footing or bearing pressure approach. So some of these do require some innovative approaches to try and kind of understand kind of how these embedded structures are working. I think it's important to kind of recognize that the PY springs, you know, if you use them on their own in programs like LPIL, FB multi-peer, or Midas, just being aware that there are other effects that start to come into play with scale, specifically over 5 feet diameter, that you may want to start thinking about and talking about with your geotechnical engineer as a way to kind of how do you account for that, and probably the best way to generally deal with that is multipliers. P multipliers or Y multipliers, something that can help you produce the response that you're thinking the geotechnical information supports. And I just want to point out that, you know, most of these software tools don't generally offer rotational spring capabilities. So really, your kind of default situation is to fall back to a PY multiplier approach. And really, I think considering the soil moment rotation stiffness, I think it's something that's important. Research seems to indicate that it's relevant and something that really should be involved in probably any size pile, perhaps. It may be naive to think that the lateral behavior of a pile in a highly complex medium like soil only is translational. You know, as these things move, there's skin frictions happening. There's a lot of different things that are going on with relation to the stiffness of the actual pile itself. So different factors in there, something to keep in mind in terms of approaching it and how you're going to model or take on something like this. And I think it's important to recognize that Midas Civil is an effective structural analysis program and solution that, you know, avoids interaction between separate programs, which a lot of programs still have. However, keeping in mind that the soil structure interaction module has some limitations and does make assumptions based on the input, and is based on PY curves. So keeping that in mind for these other effects. I think it's important, like I said, some added stiffness that could be an effect here, and keep that in mind for seismic specifically. Again, can't overemphasize that, but you know, you may be modeling some soil structure components that are giving you 10 inches of displacement when really it's only 5. And so just keep that in mind in terms of how you back calculate that and how you correlate that to your analysis for seismic, which does depend directly on displacement-based analysis. There are other things going on in the ground that will have effects on that. So from that, maybe envelope and bound the solution, which is a good idea to ensure redundancy and design for variability in the modeling that you're taking on. So by taking advantage of current soil structure interaction and geotechnical knowledge to leverage capacity of soil and embedded elements, you know, you can gain some extra mileage from these robust structures and perhaps offer them a longer life and demonstrate they can meet structural demand for current codes by taking on this more innovative approach, perhaps. You know, and soil is complex, it's highly nonlinear, and some would say unpredictable, but we think this is an appropriate approach, and we believe that the implied formulations behind it are supported by research and information that seems to lead to good results that I think are in the end optimal for these types of structures. And again, be aware there's no perfect approach and no single tool that can solve all the issues. And I think the biggest take-home message is that our geotechnical engineers are good friends, and they do offer some great insight into how we can properly take a very complex medium and turn it into something that we can adapt with our very specific finite element models and try and come up with a solution that works for everyone. So with that, just a bunch of references and credits here. Really, there's some really great information out there, and obviously I want to tip my hat to a lot of these people and the software tools that help us on a day-to-day basis deal with some really great engineering challenges. And specifically, I'd like to kind of point out a great reference here, Deep Marine Foundations, where if you want to learn about some of the amazing work being done on some of the biggest bridges in the world and how they get these caissons in, and even larger footings for the bridges in Greece, it's a great reference to kind of go to, and that's by editors by Bob Bednar and Elman Jr. So that's pretty much it for most of the information here. And I also want to say thank you to everyone for your time, and look forward to hearing input, questions, and discussion on this potentially interesting topic. And thank you.